The ratio between a diagonal and one side of a pentagon is the golden ratio. Today we're going to do a proof of this. So this is a regular pentagon which has a side length of 1. And to begin with, let's draw two diagonals. As this angle over here is also 108 degrees, these angles are both 36 degrees, as it's an isosceles triangle. Let's draw one more diagonal. These angles are also 36 degrees. So let's call the length of one diagonal x. So this is x. Now we see that in this triangle, where two angles are 36 degrees and one angle is 108 degrees, the side lengths are like 1x. So there's a similar triangle to this, which is here. So there must be the same ratio in the side lengths. The side which the 108 degrees sees is x times the other side, so these two sides are both 1 over x. Remember, the side length of the diagonal was x, so this length right over here is x minus 1 over x. Now let's find some more angles. 36, 36. This angle right over here is 72 degrees. This is 36 degrees. So this angle is also 72 degrees. And we can see that this triangle here is also isosceles. So this length, 1, equals to this length, x minus 1 over x. Now let's just solve this equation. X is non-zero, so we can multiply by x. 0 equals x squared minus x minus 1. 0 equals x minus 1 over 2 squared minus 1 over 4 minus 1. 5 over 4 equals x minus 1 over 2 squared. X minus 1 over 2 equals the square root of 5 over the square root of 4, which is 2, plus or minus, of course, and x equals 1 plus or minus the square root of 5 over 2. X is a length, so it must be positive. So x equals the square root of 5 plus 1 over 2, which you can recognize as the golden ratio. 1.618, and so on. It's because of this golden ratio hidden in the pentagons that stars are so beautiful. In this amazing fractal, there are many stars, each inside a new and smaller pentagon. But no matter how much we zoom in, we see the same view of infinitely many stars.